Myself, Shrika. Today we are doing our Exeed project based on noise reduction technologies for turbofan engines. Actually, our aim and objective of this project is fan is a strong function of the rotational tip speed and the fan ratio. The surest way to reduce fan noise is to reduce the tip speed and pressure ratio, but this causes the engine diameter to increase to recovered thrust. Engine noise is one of the major contributors to overall sound levels as aircraft operate near airports. Turbofan engines are commonly used in commercial transport due to their advantages for higher performance and lower noise. The noise reduction comes from combination of changes to the engine parameters and low noise design feature. First, our main aim is to reduce the fan noise during landing and takeoff. Introduction. The significant process continues to made with noise reduction for commercial aircraft. Since it takes many years for technologies to be developed and implemented, it is important to have aggressive technology goals that lead the target entry into service states. It is a term used to combine takeoff, cutback, and approach certification margins related to regulation noise levels. Effective received noise level is decibels in a certificate metric used for aircraft. It evaluates both the noise amplitude and duration at a single measurement point. During flyover, engine noise is one of the major contributions to all over sound levels as aircraft operates near airports. The turbofan engines are commonly used in commercial aircraft due to the advantages for higher performance and lower noise. The noise reduction comes from combination of changes to the engine cycle parameters and noise reduction design features. Engine noise sources principally come from the fan, including the stator, the exhaust, also referred as the jet, the compressor, the combustion, and the turbine. So, background of our idea is the engine noise is major contributors to our overall sound levels as aircraft operate near airports. The turbofan are commonly used on transportation due to the advantages of its higher performance and low noise reduction. So the fan noise is stronger function of the rotational tip speed and fan pressure ratio. The surest way to reduce fan noise is to reduce the tip speed and pressure ratio, but it causes the engine diameter to increase to recover thrust. Optimization studies show that best fan speed for takeoff is wherever the rotational speed is just under the Mach number 1 because to eliminate the shock associated with the noise. Once it has been achieved in the engine design, the fan driver ratio becomes controlling factor of broadband noise. The source of this noise is the turbulence in the fan, wake up strictly the status, and the resulting unsteady pressure field that becomes atmospheric waves and varies from the engine fan type. Another advantages to reducing the fan tip speed and pressure ratio in the number of noise sources are reduced, which helps make noise reduction design features more effective. Model scale fan can called advanced duct propeller ADP of an ultra high bypass ratio. Engine concept where it well showed that significant noise reduction can be achieved by lowering the fan tip speed and pressure ratio. Actually, this is the dominant source. Actually, engine was based on the main function of the turbofan engine is in inlet. It takes a sufficient or required amount of air in the inlet, and after the inlet, it compresses the air with the help of the compression. In the combustion, it compress the compressor fuel can make fine droplets and mixed with the atmospheric air, and it both combinedly form fuel and oxidizer and start burning in the combustion. And this turbine, with the help of turbine and the shaft, in the help of the combustion, the fuel is injected. The fuel is injected and burned and moves the engine forward with the help of the fan from the turbofan. With the help of the fan from the turbofan engines, the propeller moves forward. So the main disadvantages of this engine, it produces high noise during the takeoff and the landing. So these are the high ultra bypass ratio, scarf inlet, active noise control, forward swept fans, swept linear surfaces, and crevasse nozzles. And this will be continued by the teammate Sneha.
Background of this idea is several tests were done to validate the benefits of adding combinations of acoustic treatment, treatment for stall control, and the effect of containing lower the fan tip speed while maintaining constant fan pressure ratio. The results from these tests were they used the Pratt & Whitney to design their graded turbofan engine, which has the potential of meeting the 42 target. Assuming additional noise reduction concepts are applied to both the engine and the airframe. A scarf inlet can be used to reduce inlet fan noise by redirecting the forward radiated sound away from the community. Several tests were done on engines that showed significant noise reduction. Computational methods continuing to improve application to scarf inlets are expected since the optimizing the aerodynamic design for both cruise and takeoff will be the possible. Active noise control was investigated for fan noise reduction. A special fan rig called the Advanced Noise Control fan was built and used a wide range. Equators designed to cancel fan tones were mounted in fan duct walls and inside stator vents. The series of tests were performed to show single and multiple duct mode cancellation from both the inlet and exhaust of the fan duct. Strategies evolved selectively target modes that only affect directly patterns that impact community noise during takeoff and landing. Improvements have been made in noise prediction in the development of the V07222, TF fan S23, P fan S24, uh, Linflux 25 codes. That V070 code predicts the inlet and aircraft and duct sound power levels as a function of engine speed for rotors, stator interaction noise sources. It is computationally efficient since it relies on a classical unsteady aerodynamic methods but does not reliably predict the correct distribution of sound power over the range of propagating duct modes. It also does not predict noise. Supersonic tip speed fans are typically in the model of the rotor self noise. The fan T fans code couples the inlet fan, rotor stator, and nozzle and accounts for the duct linears using the impedance modes in the fragrance domain. The LFX code solves the linearized Euler's equation and can be used to replace rotor and stator source model in T-fans to model more realistic states flows. It has been shown that these codes provide better prediction power levels on mode basis and power proper trends in tone levels with varying geometric parameters such as the Saturn number. In the future, the matching methods will be used to stimulate code brand and tone noise prediction. CCA code called BAS. It has been under the development for the several years. Design and drawing of the prototype rough sketches. Conclusion. A review of recent research conducted and sponsored by NASA of turbofan engine noise reduction has been presented engine system was cycle changes fluid speed, the lower than the pressure ratio, the lower jet exhaust velocity, and the best way to achieve single noise. Further noise reduction can be realized by applying design features that reduce the noise with the minimal impact to performance. Example of these technologies as we presented include scarf inlet, active noise control, the chevron nozzles, forward sweat, fans and sweating, vaniscator, variable area nozzles, fan tailing edge bonding, soft state vanes and acoustic treatment placed over the fan. Progress has been made developing fan and jet noise prediction tools. Methods available today combine CFD and acoustic analysis and do better job of the predicting changes of geometric parameter than the traditional empirical methods. Future work is needed developing technology for both engines and airframe noise in order to meet more significant state and noise trends to near airports. References. Thank you.